Today I shall start about a chapter of class 11 NCERT chemistry, which is basic concept of chemistry. These are some basic arrangement of the particles such as solid, liquid and gaseous state. Here first one is solid state, second one is liquid state and third one is gaseous state. Here actually we learn about matter, how many types of matter there is. So matter consists of two types of substance. One is mixture and another is pure substance. Mixture is two kind. One is homogeneous mixture, another is heterogeneous mixture. And the pure substance can be divided into two parts. One is element and another is compound. This is the bend shape water molecule. This is carbon dioxide molecule. There are different atoms of elements like hydrogen, oxygen, nitrogen, copper, sodium. Two hydrogen atom will combine into hydrogen molecule. Two oxygen atom will combine into oxygen molecule. This is actually the representation of atoms and molecules. Unit of length is considered into meter, unit of mass in kilogram, gram, unit of time in second, unit of electric current is in ampere, unit of thermodynamic temperature in Kelvin or degree Celsius, unit of amount of substance in mole, unit of luminous intensity in candela. These are the symbols in SI unit of length, mass, time, electric current, thermodynamic temperature, the amount of substance and luminous intensity. Here the multiple with symbol is given in this table. 10 is called deca, and if we move upward with 10 to the power minus 1, minus 2, minus 3, minus 6, minus 9, minus 12, minus 15, minus 18, minus 21, minus 24, then it will be from deca to deci, centi, milli, micro, nano, pico, femto, atto, zepto, yocto. If we add powers in positive powers, then towards downward we can say it as deca, hecto, kilo, mega, giga, tera, peta, exa, zeta, iota, etc. Here is a weight balance instrument is given here in the right corner. Here is a beam, here is a pen, here is a rider, carrier knob. There are some instruments which are used in chemistry labs. First one is burette, second one is pipette, third one is graduated cylinder, fourth one is volumetric flask. Then there are three types of thermometers. One is Kelvin thermometer, Celsius thermometer, Fahrenheit thermometer. There are some laws in chemistry. There are 5 associated laws. First one is law of conservation of mass. Second one is law of definite proportions. Third one is law of multiple proportions. Fourth one is Gay-Lussac's law of gaseous volume. And fifth one is Avogadro's law. Let us understand by taking the example of water. Mass percentage of element is equal to mass of the element in compound divided by molar mass of the compound into 100. So molar mass of water is 18.02 gram. So mass percentage of hydrogen is 2 into 1.008 divided by 18.2 into 100%, that is 11.18%. Then mass percentage of oxygen is 16 divided by 18 into 100%, it is 88.79. Let us take another more example which is ethyl alcohol C2H5OH. Here its molar mass is 46.068 gram. So mass percentage of carbon is 52.14%. Mass percentage of hydrogen is 13.30%, and mass percentage of oxygen is 34.73%, which is calculated by the previous method. The concentration of a solution or the amount of the substance present in the given volume can be expressed in any of the following ways. Number one is mass percent of the or weight percent, W by W percentage ratio. Second one is mole fraction. Third one is molarity, and fourth one is molality. With these four we can measure the strength of the solution of the chemical substance. So mole fraction is equal to number of moles of A divided by number of moles of the solution, that is Na divided by Na plus Nb. Molarity, molarity, it is mostly or most widely used in the unit is denoted in m. It is defined as the number of the moles of the solution in 1 liter solution, that is how much moles of solute present in 1 liter solution or 1000 ml solution or 1000 cc solution. This is molarity. So molality is number of moles of solute present in 1 kg of solvent, that is 1000 gram of solvent, or it is denoted by small m in bracket. So number of moles of solute divided by mass of solvent in kg. Thank you. This is the end of the chapter 1. Next come to the chapter 2, states of matter. There are intermolecular forces, atom A, atom B. Here is symmetrical distribution of the electrical charge cloud. When it is deformated in right corner with some polarity, here polarity arises in atom A and also atom B. So atom A has instantaneous dipole, which induces dipole in atom B. So this type of dipole induced dipole interaction will create intermolecular forces, and intermolecular forces will affect on the physical state of the matter, that is gaseous state, solid state, and liquid, gaseous state, liquid state, and solid state. London forces or dispersion forces. The temporary dipoles of atom A and B attract each other. Similarly, temporary dipoles are induced in the molecules also. This force of attraction was first proposed by the German physicist Fritz London, and for this reason the force of attraction between two temporary dipoles is known as London force. Another name of the force is dispersion force. These forces are always attractive, and interaction energy is inversely proportional to the power of the distance between the two interacting particles, that is 1 by r to the power 6, where r is the distance between two particles. These forces are important only a short distance, that is around 500 picometer, and their magnitude depends on the polarizability of the particle. So the polarizability of the particle if increases, the London forces also increases, and which impact on the physical state of the matter. This is a polar axial molecule. This is a polar axial molecule, and there is another polar axial molecule, so their interaction will be dipole-dipole interaction. And in second case, if a molecule AB, which is polar molecule, but here non-polar molecule is adjacent with the polar molecule, then there will be some induction of dipole, which is called induced dipole. So here the interaction will be dipole induced dipole interaction between permanent dipole and induced dipole. This will also affect on the physical state of the matter. So dipole-dipole force is proportional to 1 by r to the power 3, and dipole induced dipole, which is called London force, which is actually proportional to 1 by r to the power 6, where r is the distance between the two molecules. Now come to hydrogen bond. It is a special case of dipole-dipole interaction. This is found in the molecules in which the highly polar NH, OH or HF bonds are present. Although the hydrogen bonding is regarded as being limited to nitrogen, oxygen, fluorine, but species such as chloride may also participate in hydrogen bonding. The energy of hydrogen bonding varies between 10 to 100 kilojoule per mole. So due to this hydrogen bonding interaction, H2S molecule is gaseous but water molecule is liquid due to the presence of three-dimensional hydrogen bonding interaction. Now come to gaseous state. First law, Boyle's law, which is known to everyone. At constant temperature, the pressure of a fixed amount of gas varies inversely with the volume. This is known as the Boyle's law. P is proportional to 1 by V. So P is equal to a constant K1 into 1 by V. So PV is equal to K1. Here two graphs are given here. One is pressure versus volume curve, which is hyperbolic curve, and another is pressure versus 1 by V curve, which is a straight line. So T1, T2, T3 are three different temperature, where T3 is greater than T2 is greater than T1. Second law is Charles' law, where the pressure remaining constant, the volume of the fixed mass of a gas is directly proportional to the absolute temperature. So V is proportional to T. So V2 by V1 is equal to T2 by T1. So V is equal to K2 into T. So the graph is given here. So volume versus temperature curve, which is a straight line. Passing through the 0 point, they all meet at minus 273.15 degrees centigrade. Gay-Lussac's law. At constant volume, the pressure of a fixed amount of gas varies directly with the temperature. So P is proportional to T. So P is equal to P by T is equal to constant K3. So P is equal to K3 into T. Avogadro's law of volume of amount. Avogadro's law states that V is proportional to N. So V is equal to K4 into N. The number of molecules in 1 mole of gas has been determined to be 6.022 into 10 to the power 23 and is known as Avogadro's constant. Now come to ideal equation, gas equation by combining Boyle's law, Charles' law and Avogadro's law. Where Boyle's law is V is proportional to 1 by P, another V is proportional to T and V is proportional to N. So combining with it that, so V is proportional to R into NT by P. So PV is equal to nRT. So it is the ideal gas equation. Now come to density and molar mass of the gaseous substance. So from ideal gas equation PV is equal to nRT, we get the equation N by V is equal to P by RT. So N by V is equal to N is equal to small m by capital M. Small m is mass and capital M is molar mass. So it is small m by mv is equal to P by RT. So small m by V is equal to density D. So molecular mass M is equal to dRT by P. Now come to Dalton's law of partial pressure. So if each gases has partial pressure like P1, P2, P3, etc. at constant temperature and volume, so P total is equal to P1 plus P2 plus P3 plus dot 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 up to N or infinity, where P total is the total pressure exerted by the mixture of the gases which has partial pressure P1, P2, P3, etc. Kinetic energy and the molecular speed. If there are n number of molecules in a sample and their individual speed are u1, u2, u3 dot 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 up to un, then the average speed of the molecule is equal to u average can be calculated as follows. U average is equal to u1 plus u2 plus u3 plus dot 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 un divided by n. So there are two curves here given, Maxwell-Boltzmann distribution of speed curve. Here two curves are seen here with different peak, but the area of the curve is constant. Two different curves at two different temperature T1 and T2 is given here. With increase of temperature, the probability, the most probable velocity of the molecules of maximum number come to increase. So the curve gets flattened. So the number of molecules moving with higher speed increases with increasing temperature. So this is explained with this curve of the distribution curve of the gas molecules. We know that the kinetic energy of the particle is given by the expression of 1/2 mu square. So the translational kinetic energy is equal to half mu bar squares, where u bar is the average velocity, u bar square is the u bar square is equal to u1 square u2 square plus dot 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 un square divided by n. The mean square speed is direct measure of the mean square speed is direct measure of the average kinetic energy of the gas molecule. If we take the square root of the mean of the square root of the speeds, then we get the value of the speed which is different from the most variable speed of the average speed. This speed is called the root mean square speed, which is given by the expression of URMS. URMS is equal to root over of u bar square. Root mean square speed, average speed, and the most probable speed have following relationship. URMS is greater than U average greater than U average. URMS is greater than U average greater than U most probable speed. So these are two PV versus P curve and pressure versus volume curve of the real gases like hydrogen, carbon monoxide, methane, helium, etc. The ideal gas curve is parallel to the P curve, but the real gas is not like ideal gas curve. It behaves different way. Here is a sharp dip at the initiation of this curve for carbon monoxide and methane, and there is a sharp increase in H2 and helium. Two wrong assumptions from the kinetic theory. There are two wrong assumptions in the kinetic theory that there is no force of attraction between the molecules of the gas. The volume of the molecules of the gas is negligibly small in comparison to the space occupied by the gas. Pressure correction. Now P total is equal to P real plus A n square by V square, and the volume correction V total is equal to V minus NV. Here A is a constant. So Van der Waals equation is P plus n square A V square V minus NV is equal to nRT. The deviation from ideal behavior can be measured in terms of compressibility factor Z. Compressibility factor is Z is equal to PV by nRT. So V total is equal to nRT by P. So on putting nRT by P in this equation, we get Z is equal to V real by V ideal. So Z versus P curve is shown here for the ideal gases, ideal gas and along with the real gases. Here in Z versus P curve, there is a dip in the initiation of the curve of carbon dioxide, methane, oxygen, nitrogen, but there is no dip at the initiation of the curve of hydrogen and helium. Now come to liquefaction of gas. Andrews noticed that at high temperature isotherms looks like that of an ideal gas. An ideal gas cannot be liquefied even at very high temperature. As the temperature is lowered, the shape of the curve changes and the data show the considerable deviation from the ideal gas behavior. Here from the Andrews curve we get the critical temperature along with critical volume along with critical pressure, which is denoted as Tc, Vc and Pc. Isotherms of carbon dioxide at various temperature is given here. This is vapor pressure versus temperature curve of some common liquids. Now come to surface tension. Surface tension is a quenching of the surface of the liquid phenomena. Its reason is a molecule in the bulk of the liquid experiences equal intermolecular forces from all sides. The molecule therefore does not experience any net force, but for the molecule on the surface of the liquid, the net attractive force operates towards the interior of the liquid, and due to this the molecules below the surface gets tensed. Since there are no molecules above it, so liquid tend to minimize their surface area. The molecules on the surface experience a net downward force. So this quenching of the surface of the liquid phenomena is known as surface tension. Now come to viscosity. Viscosity is retardation of the flow of the layers of the liquid present. If the velocity of the layer at a distance dz is changed by a value with du, then the velocity gradient is given by the amount of du dz. So a force is required to maintain the flow of the layers. This force is proportional to the area of the contact of the layers. So that is capital F is proportional to A, which is area of contact, and force is also proportional to du dz, velocity gradient. So the equation we get F is equal to eta A du dz. So eta is equal to viscosity constant. Now eta is proportionality constant known as coefficient of viscosity or viscosity coefficient. Viscosity coefficient is the force when velocity gradient is unity and the area of constant is unit area. Thus eta is the measure of the velocity. SI unit of the velocity coefficient is Newton second meter square, which is Pascal second. In CGS system, the unit of the coefficient of viscosity is poise. 1 poise is equal to 1 gram centimeter inverse second inverse. That is 10 to the power minus 1 kg meter inverse second inverse. The greater the viscosity, the more slowly the liquid flows. The hydrogen bonding and the van der Waals forces are strong enough to cause higher viscosity. Glass is extremely viscous liquid, so it is so viscous that many of its property resembles with solid. Viscosity of the liquids decreases as the temperature rises because the high temperature the molecule have high kinetic energy and can overcome the intermolecular forces to slip past to another between the layers. Okay, thank you. This is the end of this chapter.